Right now, while you're watching this, parts of the continents you live on may be getting quietly stolen from underneath, dragged away through hot rock you'll never see. And the wild part is that this hidden theft can light volcanoes in the middle of the ocean, where, on paper, no volcano should exist. So if you've ever wondered how a lonely volcanic island can pop up far from any plate boundary, stay with me, because the answer isn't just at Earth's surface, it's in the deep roots of continents. And the story plays out on timescales so slow they're almost impossible to imagine. To get oriented, picture Earth like a layered engine. The crust is the thin, brittle shell we stand on. The mantle beneath is mostly solid, but able to flow very slowly over millions of years. And deeper still is a metallic core whose motion helps generate our magnetic field. The outer part, called the lithosphere, is broken into tectonic plates that creep along at roughly the pace your fingernails grow, and where plates collide, pull apart or slide sideways, we get the classic headline makers, earthquakes, mountain ranges, and many of the world's volcanoes. At convergent boundaries, plates move toward each other and the crust shortens, sometimes building huge mountains, and in many places an oceanic plate dives downward in subduction, carrying water-rich minerals that help trigger melting and feed volcanic arcs. At divergent boundaries, plates separate and the mantle rises to fill the gap, melting as pressure drops and building new oceanic crust along mid-ocean ridges. At transform boundaries, plates grind past each other, storing and releasing stress in powerful earthquakes. That's the standard map of how Earth works. But here's the plot twist that makes the open ocean volcano mystery so interesting. When a continent begins to break apart, the breakup may not be limited to the rift you can trace on a map or the cracks opening at the surface. The continent has deep roots, a thick, strong, chemically distinctive part of the lithosphere that extends down into the upper mantle. And when tectonic forces stretch a continent, the mantle below doesn't just sit there like a calm basement. It responds, circulating and reorganizing in ways that can slowly strip material from the underside of the continent. Think of it less like a clean snap and more like peeling paint or shaving thin slices off the bottom of a very thick board. Over long periods, patches of continental root can detach, and once those fragments break free, they don't have to fall straight down like a rock in water. The mantle is moving, slowly but relentlessly, so pieces can be transported sideways, carried away from the continent and beneath nearby oceans, sometimes travelling incredibly far from the place where the breakup started. And now we arrive at the key clue scientists use like a fingerprint at a crime scene: chemistry. Continental rocks tend to be enriched in certain elements compared with the more uniform rocks that typically dominate the oceanic mantle. So if you mix even a small amount of that continental root material into the mantle beneath the ocean, you can change the flavour of magma that later forms there. It's like adding a spoonful of a strong spice to a big pot. Most of the pot stays the same, but the taste changes enough that you notice. When mantle with that extra enriched ingredient partially melts, the melt rises because it's buoyant, collects, and can eventually erupt, forming seamounts and islands whose lavas carry chemical signatures that look surprisingly continental, even though they erupted through oceanic crust. This matters because, for years, many odd oceanic volcanoes were often explained mainly by two big ideas: subduction recycling, where sediments and oceanic crust get pushed down at trenches, altered, and later contribute to new magma, or deep mantle plumes, hot upwellings rising from far below that can generate volcano chains. Both processes are real in many places, but they don't explain every observation equally well, because some volcanic regions sit far from subduction input, and some don't match what we'd expect if a superhot plume were the main engine. The continent root peeling idea adds a third pathway. Continents can seed the mantle with enriched material during breakup, and that seed can keep influencing volcanism long after the continents have already separated at the surface. In other words, a breakup isn't just a moment, it's an aftershock that echoes through the mantle for tens of millions of years, because mantle flow keeps moving, remixing and transporting those enriched fragments beneath new ocean basins. You can imagine the surface breakup like tearing a thick sticker off glass. The visible tear happens fast, but underneath, adhesive residue can smear farther than you expected, and long after the sticker is gone, that residue still changes how dust sticks and how light reflects. Similarly, long after a new ocean opens, the mantle beneath can still carry residue from the continent's deep roots, and when conditions are right, temperature, pressure and the right amount of melting, that residue shows up at the surface as volcanoes that look out of place. Zooming out, the bigger message is that Earth's mantle isn't a perfectly mixed soup. It's a slow, dynamic system with recycled streaks and patches, some from subducted slabs, some from ancient mantle domains, and yes, potentially some from peeled-off continental roots. So when magma forms, it can inherit a history written over hundreds of millions of years. This also changes how we think about continents themselves. They're not just rigid rafts floating above a passive interior because the interior can nibble at them from below during rifting, and that hidden process can export continental material under the oceans, where it becomes the unexpected fuel for future eruptions. So, the next time you see a tiny dot of land in the middle of a vast ocean, remember that it might be the surface expression of an ancient breakup event, an island built from magma whose ingredients were quietly stripped from a continent's deep foundation long before humans existed. And if that sounds almost unbelievable, that's exactly the point. Earth's most important transformations often happen at speeds we can't feel, in places we can't see, leaving clues in chemistry and geology that let us reconstruct the planet's hidden motions, like a detective reading a story written in stone.